These are additional examples of kinetic friction that highlight the important distinction that friction is always opposite motion, not the applied force. On the left, let's say that Superman is just doing his thing, patrolling the city, when he sees a heavy 30-kilogram box blocking the road. Superman pushes the box to the right with an applied force of 300 newtons, and it begins moving. If the coefficient of kinetic friction between the box and the road is 0.7, calculate the kinetic friction force between the box and the road while it's moving. Take a moment, pause the video, and see if you can solve this problem for yourself before moving on. I'll begin by drawing my interaction diagram, being very careful to show the frictional force and the normal force between my surface, in this case the road, and the box. I'll go ahead and highlight my box here. I'll begin by drawing a force diagram as well. All right, and I've gone ahead and drawn my force diagram, again showing the normal force pointing up, the gravitational force on the box, or the weight of the box pointing down, and these are equal to each other because the box is not accelerating vertically. My applied force pointing to the right, applied by Superman on the box, and my kinetic frictional force pointing to the left because the box is moving to the right, okay? I drew my frictional force to the left because the box is moving to the right, not because Superman is pushing it to the right. In this case, Superman is pushing the box to the right, and it begins moving to the right because the box was not moving before. So just make sure you're clear about that. I've also drawn the force of friction arrow shorter than the applied force arrow because I know that the box is moving, and therefore there must be a net force because the box is accelerating really to the right. The applied force must exceed the kinetic frictional force here. And so as always, I'll write out the sum of forces in the both horizontal and vertical directions. In this case, the sum of forces in the x direction. If I call right positive, let me go ahead and denote my coordinate axis here. I'll call right and up positive. Then I know that the applied force minus the frictional force, the kinetic frictional force, would be equal to the mass of the box times the acceleration of the box in the x direction. And in the y direction, that means that the normal force minus the gravitational force is equal to the mass of the box times the acceleration in the y direction. There is no acceleration in the y direction because it's not it's not accelerating up and down, so that's equal to 0. I'll also write out my expression for the kinetic frictional force. In this case, that is equal to the coefficient of kinetic friction times the normal force. And I'll also write out my weight force equation. I'll start doing that just so it's very explicit that we have all of our expressions out at one time. Now, I'm looking for this F sub k. So I can get that either from the Newton's second law equation or from this equation directly, right, the expression that I have. If I look at the Newton's second law equation, I don't know the acceleration of the box. So it's going to be difficult to use Newton's second law to solve for the frictional force. But what I can do, right, is if I already have the coefficient of kinetic friction, I just need the normal force, right? And I see the normal force is right here. I can calculate the weight force, and this is equal to 0. So I can use, I'm going to say my plan, right? We're going to call this equation 2 here. Use equation 2 to solve for Fn. Then if I call this equation 3, plug Fn into 3, right? It's always important before you solve anything to have a plan to make sure what you're doing will get you what you want. So I'm going to go ahead and do that then. If I rearrange equation 2, Fn minus Fg is equal to 0, right? We've seen this before a few times. So Fn is equal to Fg, which is equal to the mass of the box times g. So that means that Fn is going to be equal to 30 kilograms that was given to me times 9.8 meters per second squared, which is 294 newtons. So then I can go ahead and plug that into equation 3 here. I'll go ahead and show that over here. I'll say then that the force of kinetic friction is equal to the coefficient of kinetic friction, 0.7, times that normal force, 294 newtons, and that'll be equal to 205.8 newtons. Awesome. All right, now let's take a look at the problem on the right here. Let's say Superman continues about his day when he sees a speeding train that has lost power and cannot brake. Oh no. Superman starts pushing against the train. Let's assume for this problem the train is traveling leftward and Superman's pushing to the right. And he pushes with a force of 1,000 newtons. If the train has a mass of 90,000 kilograms and the coefficient of kinetic friction between the wheels and the tracks is 0.3, what is the acceleration of the train? All right. Now, I know it's asking for the acceleration, and I know that to do that, I'll probably need to use Newton's second law. So what I'm going to do is essentially the same process. I'm going to draw an interaction diagram, a force diagram, and then I'll write out my sum of forces. You'll notice the interaction diagram for this looks essentially the exact same as the one with the box, right? We have the same number of objects, the same types of forces. All right, I've indicated the normal force pointing up and the gravitational force pointing down, which again, in this case, and in many of the cases we've looked at so far, are equal, but again, they won't always be. And now, let me ask, right, if Superman is pushing to the right, then I will go ahead and show that force as so. I will show that applied force, and that's 1,000 newtons. Now, to draw the force for friction, I need to ask myself, which direction is the train moving in? The train is moving to the left. So if the train is moving to the left, I need to show the force of friction pointing opposite or to the right. So in this case, we have two forces pointing to the right. Remember, friction always opposes motion, not the applied force. Because the train is moving to the left, then friction is going to act opposite its motion or to the right. And in this case, it's important to note that the train has lost power, so there is no forward thrust from the engine. The train is not propelling itself forward in any manner. And there is no brake force as well we need to worry about. Okay, just like before, I'll write out the sum of forces in the x and y direction, and I'll express my kinetic friction force and weight force as well, just so I have all my equations in one place. So in this case, the sum of forces in the x direction will actually be the applied force plus the kinetic frictional force, because they're both pointing to the right, and I'm calling right positive. And that's equal to the mass of the train times the acceleration of the train, which is actually what I'm interested in, so I'll hold on to this for a second. I'll also write out the sum of forces in the y direction, which again is equal to the normal force minus the gravitational force, which is again equal to 0 because the train's not accelerating vertically. And so from here, I'll also express my, again, just for simplicity here, I'll express my, just nice and, it's always simpler to have everything in one place. All right. Now, what I'm looking for is this AX, right? So let me ask myself, do I have the mass of the train? I do. Do I have the applied force? I do. Do I have the kinetic frictional force? I don't. So I need to get this. How can I get this? Well, let me come down here. I can get the frictional force by taking the coefficient times the normal force. Do I have the normal force? No. How do I get that? Well, I can come up here and use this equation to get the normal force. I know the weight, and I know they're equal to 0. So my plan looks like this. I'm going to use equation 2 to get the normal force. I will then use that normal force in equation 3 to get the kinetic frictional force, and then I will use that for equation 1 to get my acceleration in the x direction. So then that means the normal force minus the gravitational force is 0. The normal force must be equal to the gravitational force then in this case. That means the normal force is 90,000 kilograms times 9.8, which is 882,000 newtons. Then, using equation 3, the force of kinetic friction is 0.3, the coefficient of kinetic friction times the normal force, which is 882,000 newtons, which will give me a frictional force of 264,600 newtons. Okay, almost there, almost there. Now, if I were to rearrange the first equation for AX, I'll do it like so. If F applied plus FK is equal to m train A, then that means that A must be equal to the applied force plus the kinetic frictional force divided by the mass of the train. And if I were to plug those values in, I'm running out of room here, but I'll show that down here. That's the applied force was 1,000 plus this kinetic friction force, 264,600 divided by the mass of the train, which was 90,000. And again, the units will work out here. So that will be equal to 2.95 meters per second squared. Whew, we did it. All right. So even though this problem was a bit complex, what I really want you to keep in mind is this idea, that the force of kinetic friction is opposite motion, not opposite the applied force, right? That is what this example was hoping to illustrate. So whenever you're solving a problem, it's helpful to draw a sketch as well, which I haven't done, but if it helps to draw a sketch, think about what's happening, right? And ask yourself, which direction is the object traveling in, and indicate friction opposite that direction. Right, you'll notice in both cases, Superman is pushing to the right, But on the left, the box is moving to the right, and on the right side here, we have the train is moving to the left. And so the force of kinetic friction you'll see are in opposite directions in these two problems. All right.